So the first topic we're going to cover is biomechanics. So this should be a quite popular topic for most individuals because it combines the application of physics with the human body. So in terms of biomechanics, there's two different types that we'll be looking at. There's biostatics and there's biodynamics. So just from the words themselves, static means no motion, dynamic means motion. So we're going to analyze everything at equilibrium first and then move on to analyzing things in motion next week in lecture 2. So for this lecture, I'm going to start off with a quick recap and then go straight into an introduction to biomechanics. So basically talk about the differences between biostatics and biodynamics. And this lecture purely focuses on biostatics. And with biostatics, there's a lot of concepts from static equilibrium. So knowledge from Physics 111 or Physics 121 would be very helpful, but they're not prerequisites for this course. So I will be going through an overview of forces, torques, as well as work, energy, and power, just so that everybody's up to speed with all the math that we have to do. And of course, if you're struggling with any part of it, don't hesitate to reach out. So after we've gone through a brief overview of forces, torque, work, power, and energy, I'm going to go through some applications and examples of where we can apply those physical concepts to the human body. So in terms of static equilibrium, that would most likely be, for example, how I can hold my head up straight and keep it still. I can go through muscles in terms of tension, muscles contracting and expanding in order to hold, let's say, a weight on my hand, and then how much power is involved in me exerting that energy to hold something up. Afterwards, we'll finish our lecture with a discussion about bones and how they're good as cantilevers or beams with articulating joints on your body. So this lecture is very much similar to a kinesiology-based topic. So for the recap, I just want to go through what is biophysics. So what are some of those take-home messages from before? So in terms of biophysics, it is an interdisciplinary science. It applies physics-based approaches and methods to study biological phenomena. So it covers all the scales of biological organization. You have things going from the atomic and molecular scale, then to cells, and then to organisms, and then to biospheres and populations. So biophysics spans all types of biological organizations, and it's just a matter of how do you approach each of those problems with a different physical perspective. So in general for this class, we are focusing on two subsets of biophysics. It's systemic biophysics, which really has to do with the different parts of the human body. So for example, we're starting with biomechanics. Afterwards, we have hearing, we have vision, and all to do with the body itself. Afterwards, we're going through to cellular and molecular biophysics. So things that the eye can't obviously see. Things such as protein, lipid interactions, and then basic self-assembly. In terms of what we talked about last lecture, most important thing is that a living organism has three main features. It's an open system, so it always exchanges matter and energy with its surroundings. It can self-regulate, and it can also self-reproduce. So those are the three characteristics of a living organism that we've covered. And with all of our discussions from the previous class, one of the take-home messages is that a living organism requires a constant input of energy in order to survive. And in order to survive, it means that we have to try and maintain a low amount of entropy, because everything usually tends towards a state of higher entropy, which would produce complete disorder. So let's start off with an introduction to biomechanics. Biophysics is probably one of the most important branches of biophysics. Here you get to explore the effect of mechanical forces on living systems. So the question is, what kinds of forces? So you'd be looking at the effects of forces such as gravitation, elastic deformations, and friction forces. Once we understand these forces that are acting on our body, what we can do is then look at determining and understanding the movement of animals in air, land, and water. So different aspects of locomotion that we're going to be talking about in the next lecture, not this one. So in other words, what we can do is think of biomechanics as the science of movement of living organisms. In terms of how broad biomechanics is, you can apply it to so many different fields. The most obvious application for biomechanics is kinesiology, where a huge part of it is studying how your muscles, your bones, your tendons, and your ligaments work together to produce some sort of movement. So that is what we're going to be looking at in a lot of detail for this lecture, but not locomotion or movement, mainly just things in static equilibrium. There are also additional applications of biomechanics. So in keeping with the analysis of human movement, it makes sense that biomechanics is an integral part of tissue engineering and orthopedics. So what this means is you'll have to understand the structure and organization of any sort of tissue within your body in order to try and mimic its physical characteristics through engineering. So in terms of the applications, you would be able to use tissue engineering and have orthopedic implants that will be able to function correctly after they're implanted. Last but not least, something that I'm not very familiar with, but I know that studies have been done on this. Biomechanics actually has a significant subdiscipline in plant biology, or something called plant biomechanics. One can actually study the structural stability of a plant's organs, and in some cases, you can also study when plants or fruits expel their seeds from their body. So biomechanical studies can provide additional insight on how that mechanism works. So in terms of biostatics and biodynamics, the question is, which one should we start with? Obviously, it makes sense to start with something that's easier. So we're going to start with biostatics first, when everything is perfectly in equilibrium. And then we're going to upgrade and move on to what happens when bodies are in motion. So I have two pictures here, biostatics and biodynamics. With biostatics, the definition is it is the study of forces that are responsible for stationary mechanical equilibrium of a living system. So I have a picture of somebody lifting weights. So when you're lifting weights, you're going to have to hold that weight above your head or at a specific position, and you're going to produce tension and stress in your body. But your entire body isn't moving, it's still. So that's biostatics. With biodynamics, we're going to be studying how a living system can move. Terminology is locomotion through physical explanations. So basically, we'll be talking about how objects move through water, through air, and how people run. Okay, so moving on to biostatics. First going to introduce what biostatics is, but not a general explanation. I want to be able to define biostatics and determine when something is in static equilibrium. Afterwards, the rest of the main content is focused on background information so that you can understand the applications and examples that we're going to go through after. So one of the most important things is understanding how to draw free body diagrams and being able to analyze forces and torque on a system. You should also be able to understand work, energy, and power. So between all of that, it would be good for you to review that information prior to attempting any of the practice problems. So what is biostatics? Biostatics is a branch of biomechanics that studies systems that are in two states. Number one, the condition is that it's in equilibrium. What equilibrium means is that all the forces balance out so that there's no net force moving in a certain direction. So there's usually a net force of 0. With biostatics, because the object is either stationary or at equilibrium. Even though the forces balance out, it doesn't mean that the object isn't moving. So the object can either be at rest or it can be moving at a constant speed without acceleration. So this is something we're going to talk about next with Newton's second law and force equals mass times acceleration. But keep in mind that biostatics means that the object is in equilibrium, and it means that there is no acceleration. When we take a look at biostatics, we can't really just take a look at biostatics at the cellular level because your cell never stops moving. So we have to take a look at the entire living system as a whole. And when we do a problem with biostatics, we have to assume that the object or the living organism is at static equilibrium. So examples of biostatics applications, I've listed a couple here. There's the equilibrium posture of an entire body. So the fact that I'm sitting here right now, with good posture, I'm keeping myself at good posture instead of slouching down on my chair. That takes effort on my part in terms of being able to balance all of the weight that I have from head to toe, as well as the vertebral stress on my spine. The other application would be holding a weight. So if you're weightlifting or just grabbing something, you're going to hold it and not let go. So you're going to be using muscle power. And because of that, we're also going to talk about tension and stress in muscles when they're at equilibrium. So this is a biophysics course. So when we talk about any sort of living system, we have to consider the physical concepts behind it. So the conditions for static equilibrium, so any one of those biological applications I went through before, there are two conditions we have to consider for static equilibrium. Number one, if an object or a living system as a whole is in static equilibrium, number one, it's not moving, and that means there's no translational motion. If there's no translational motion, it means that all of my forces are going to balance out in the X and Y direction. So that means that the net resultant force acting on my body is zero. And that's called translational equilibrium, because that means that there is no movement or no translation in the X, Y, or Z direction. Next, the other possible type of motion that I could have is rotation. So if I'm in static equilibrium, I can't move, which means I can't shift my position, and I also can't rotate. So that means I'm in rotational equilibrium as well. Those two combined together give us static equilibrium. With translational equilibrium, we're looking at forces that are acting upon our body in one direction. When we take a look at rotational equilibrium, we have to consider all of the torque, basically the rotational equivalent of force that's acting on our body to cause rotation. So I have to go through a quick review of forces, especially for those who are not familiar with forces or haven't seen forces before. A force represented by F, and the arrow on top just means it's a vector. A force is a vector quantity that changes the motion of an object. So if I'm pushing something forward, then I'm applying a forward push in the forward direction. From Newton's second law of motion, we have an equation that's quite popular. You've seen it before. It's F equals ma. That means it's force equals to mass times acceleration. What this means is the greater the mass that you have and the faster you're accelerating, the greater the force that's required to have that motion. So on the flip side, you can also explain it as the greater the force you apply to an object, the faster it's going to speed up. And the greater the force you have, the more mass and weight you can move. But if we consider gravity, So the gravitational constant is 9.81 meters per second squared. If we consider the gravitational acceleration as a equals g equals 9.8 meters per second squared, then I'll be able to calculate the weight of a specific object. So the force of myself, for example, acting on the ground, that's going to be equal to mass times acceleration. The acceleration for an object vertically is going to be gravity. So I have F equals mg for weight. Next, it's really important that you know how to draw a free body diagram. So a free body diagram, or FBD, is a representative diagram with a bunch of arrows representing what forces act on your body or on the object and in what directions. So I just want to briefly draw something here. So usually we would have the ground like this. So you have your ground, and you usually have an object on the ground. We'll just draw a box. It has a mass of m. And in terms of what this object experiences in terms of forces, there are several things. Number one, there's the force of it pushing down on the ground. So that's going to be Fw, which I've named here. It could be Fg as well. So that's equal to mg. Next, you also have the ground pushing back up on the object. So you have N, which is called the normal force. Let's say that you have somebody on the left side pushing the object towards the right. Then that means that the person is applying a push towards the right side. So we'll call this F push. So that's the amount of force that the person is supplying in the right direction. Something else that you can add as well, what happens if there's friction between the object and the ground? If there's friction, then that means friction always acts against the direction of motion. If I'm pushing the object towards the right, then there's going to be a retarding force, or a force that takes some of that effort away. So that means if there's friction between the object and the ground, it's going to go in the opposite direction. We'll call this force of friction, F. So all of these are different forces. That itself is a free body diagram, basically a diagram that lists all of the forces with arrows as to where the forces are acting upon. Okay, so now I want to go through torque. So we already went through forces, and forces have to do with translational motion. So I can push something left or right, forwards, backwards, up and down. It's translational motion. Any force that I apply can cause a shift in where the object is. But when we look at torques, it's another type of force. It's basically a force in the rotational world. So a way of looking at it is just a torque being the tendency of a force to rotate an object around a pivot point or an axis. So when we talk about torque, we represent it using the letter tau. And then we want to see how much of the force acts perpendicular to the moment arm. So what this means is if you have, let's see, let's say that you have an axis over here and you have a door. Okay, so with that door, would it be more effective to apply a force this way, if you want to be able to swing it around that that axis point, or would it be more effective to apply a force this way? Just using logic and your own experience, it makes sense to apply your force this way. And when I apply a force right there at this location, I have a distance away from the axis that I call the moment arm. And so this we call R. And the magnitude of R is basically the distance from where you're applying the force to the central axis of rotation. So that's R. Let me erase this. I do want my force to be over here at this red dot. So if I apply a force over here, then now I can start my analysis. If I apply a force at this red dot, I want to see how much torque I have. Keep in mind the force that I'm applying is still translational. It's still a forward push, but there is going to be a rotational equivalent of force called torque, and torque is going to be defined as a cross product. But you don't have to know what a cross product is. You just have to know that a cross product is equal to the magnitude of R and F times sine of theta, where theta, let me just write this down. Theta is the angle between the two vectors. Oops. The two vectors R and F. So what this means is if I have sine of 0, that's going to give me 0. If I have sine of 90, it's going to give me 1. So when we talk about torque, it tells me that if I'm applying a force that's directly perpendicular to the moment arm, or R, then I'll get maximum torque and maximum rotation. So here, with the diagram that I've drawn, it makes sense that if I apply a force directly at the door, I'm going to give it maximum torque. Now, in some cases, you might not apply a force directly perpendicular. You might apply a force. So this would be example number 1. So this is like case number 1. In this case, you really just have tau is equal to RF. So you have RF. Sine of 90. And that gives you RF times 1. So there you have maximum torque. Now with case number 2, we'll use the exact same thing. Maybe we have our hinge here for our door. Let's apply a force, also in the same location. It means that we're going to have R going this way. But what happens if I don't apply my force directly at the door? Maybe I apply my force a little bit slanted. Let's say I do this. I apply my force like this. Now, that means there's a theta at play. And that theta must be the angle between the two vectors when both the vectors start at the same location. So if I were to draw this again, I would have this over here as my axis. I would redraw the moment arm R like this. And I would also have to draw my force vector. So my force vector, I want it all to start from the axis. I draw the force vector this way. and my theta is going to be in between the two vectors. So then I'll be able to calculate how much of the force that I'm applying is perpendicular to the moment arm, and how much that helps supply a torque to the system. So in this case, I have tau is equal to, we'll just use RF sine theta. Now we have something that is going to be less than RF, which is the maximum. We now want to go through a quick review of work and power and energy. So in terms of work, if we apply a force over a certain distance, what we're doing is work. We're providing we need energy to be able to push an object over a certain distance. Work is just a type of energy. We represent it as W. The amount of work that is done is going to depend on, number one, how much force you're exerting, as well as how far you're pushing the object. So in terms of the equation for work, we use the dot product because we want to be able to determine how much of the force acting in the same direction as displacement will contribute to work. So in this case, we use the dot product. The difference between the cross product and the dot product is really just the use of cosine and sine. With the cross product that we talked about before for torque, note that the maximum value was obtained when the two vectors were perpendicular, which makes sense for a rotational motion. Now with this, we want maximum work when both the vectors are aligned. So that means we have to use cosine. So cosine of 0 is going to give us 1, and cosine of 90, so anything that's perpendicular, is going to give us 0. So if you're pushing an object if you're pushing an object towards the right and it's moving up, then the work that you do in the direction of movement is going to be 0. So in terms of drawing this out, I have my ground here and my object. So there's my object at the beginning. So this would be initial. And so it starts over here. We'll just use the center as the point. Starts there with DI. And after a certain amount of time, we're going to push it. So we apply a certain force, and the object moves. So it moves a distance of delta x, which is from here to here. That's delta x. And that's where our object stops. So in terms of this diagram, it's showing us we have applied a force F across a distance of delta x, and that's going to be able to tell us how much work we've done. And in terms of work, work is always in units of joules. Okay, so apart from work, like I said, all you have to do is just remember the equations and know how to use them. So work is equal to force times distance. If your force and your distance are not in the same direction, then you can use cosine of theta and use the exact same method that I used before for torque. So now that we have work covered, we can go through power. So power basically is how much work is done over a certain amount of time. So you just divide the work by T for time. The units are joules per second. And keep in mind, power is going to be the amount of energy over some sort of time. If I'm looking at the power of how much work I'm doing, then I divide work by time. If I'm looking at, for example, later on we'll look at muscle power. If you're looking at muscle power, it's not just work that the muscle is doing, it also has heat generation. So when I'm looking at the power of muscle movement and muscle contractions, I have to consider the total energy of work as well as heat combined and divide that by time. Okay, so now that we have some of the background information out of the way with forces and torques and work energy power, we can finally move on to examples and applications. So there's 3 different applications I want to talk about. The first one is tension in your body. So this is the perfect application for getting to know how to practice with forces and torque. Because if we're trying to support our head, for example, on top of our spine, then that means that we're going to make sure it doesn't rotate or swivel, and we also have to make sure that it doesn't move. So we're going to take a look at static equilibrium. Okay, so in terms of supporting our heads are stuck on top of our cervical vertebrae. So there's a couple of, let's see. So over here, just gonna draw on this, you have your C1 vertebrae, and that is the topmost vertebrae on your spine that's going to help support your head. So your weight is going to be balanced by, number 1, the force that's being exerted by the C1 disc, and also by some extensor muscles at the top of the spine. So when we're taking a look at static equilibrium with this head, we have to think about what kind of motion is possible and then be able to balance everything out mathematically. So taking a look at this picture, what kind of motion is possible? Number 1, we could have translational motion. We can move our head up and down, all that kind of shifting motion. And we have to balance forces that way. Next, I can definitely swivel or rotate my head, and we're going to analyze that through torque. So we also want to make sure that torque is balanced and there's a net torque of 0. That way I can keep my head straight and still. So the question is, how do we keep our head still in an erect position, just like as you're watching this movie or video? Number 1, there is an extensor muscle over here that provides counter torque, so it prevents us from tilting our heads or swiveling. This muscle that we have is also going to experience tension. So we're actually going to be able to calculate the tension in that muscle if we have some values and constants to work with. Next, you have your C1 vertebrae. That's going to experience stress because it is holding up the weight of your head. So we'll be able to figure out how much force per unit area of stress it's withstanding. So practice problem 1.1, I won't be going through the solutions in this video. I want you to try and work it out yourself with different peers in the class. And then I'll be taking it up during the live lecture. So using the provided sketch and the following assumptions, I want you to try and determine the tension that's in your extensor muscles, as well as the stress on your C1 vertebra. So number 1, we note that the mass of the head, let's see where the cursor went. So the mass of the head is 4 kilograms. And that means that there's a certain weight of your head sitting on your C1 vertebra. We can assume that the C1 vertebra has a disc area of 4 centimeters squared. In terms of the head isn't exactly straight, like exactly above your C1. You also have additional features of your head that makes its center of mass slightly off where your spine is. So in this picture, this would be your C1, and the weight of your head is acting 5 centimeters away from the central axis of your C1, of your spine. So keeping that in mind, we then take a look at the extensor muscles. The extensor muscles are acting on the right side, 4 centimeters away from the spinal axis. So if I take a look at this, I have to be able to figure out something to do with static equilibrium. The first step to do is to draw a free body diagram of all the forces acting on the system, and then analyze all of the requirements for static equilibrium. One of the first hints that I can give is when you're drawing the free body diagram, this, especially for torque, you have a weight or a mass that's acting on the axis on the left side, and then you also have tension acting on the right side. So between the two different forces acting on either side of something that can tilt, you most likely will have to use analysis of torque to start off. Okay, so now I want to move on to the next application, which is one of the most important applications in biomechanics. It's muscle and muscle contractions. So because so much of biomechanics is based on movement of the body, you cannot move without your muscle tissue. So we're focusing quite a bit on the structure and the characteristics of different muscle tissues, and then fine-tuning our studies to skeletal muscle composition, and then taking a look at muscle contraction. Once we have a good overview of the different processes of muscle contraction, then we can move on to being able to take a look at quantifying muscle power as well as mass-specific muscle power. So that's how much power your muscles can actually provide to a system. So first of all, an overview of muscle tissue. There are two main types of tissue. There's soft tissue and there's hard tissue. Hard tissue would be bone. We're going to talk about that next. But muscle tissue is a soft tissue. And obviously it makes up muscles in human bodies. What muscles do is they contract to apply forces. So we can consider them to be machines that convert energy from the food that we eat to the mechanical energy that we use for motion. In terms of muscles, a key difference to note is that even though your muscles are contracting and relaxing, I can still be in static equilibrium. So whenever we're taking a look at muscle contraction, for example, if I'm holding up this pen right here, I'm contracting my muscles to hold up the pen, but my body is still rigid and it's still in static equilibrium. So it's very important to note that even though we're using muscles to contract and to move, your body can still be in equilibrium. So in that respect, when we take a look at muscle contraction and static equilibrium, we're only looking at what happens when the forces and torques are balanced. If they're actually imbalanced, we consider biodynamics, and that's locomotion. And at that point, we call muscle tissue myopropulsive tissue because that's the tissue that's going to help your body move versus help your body stay still. Now, we have 3 types of muscle tissue. We're only focusing on skeletal muscle tissue, but it's still good to know the differences between all 3. You have skeletal, smooth, and cardiac. So at the very top, I have a picture of skeletal muscle tissue, which is striated. you can kind of see just all the striations and all the strands that are in the real life image, as well as on the right, the cartoon image. Now we also have smooth or non-striated muscle tissue, and they look more like elongated cells that are just pieced together with no space in between. So those are smooth muscle cells. You also have cardiac muscle cells or muscle tissue, and those are quite irregularly shaped with a lot of branches that connect to each other. So just note the differences between the different types of muscle tissue, and that's all you have to know. Let's go to the next slide. Now we're just going to focus on skeletal muscles. So the first thing to understand is what it's made of. When we're taking a look at a muscle, at muscle tissue, at an entire muscle, it's just many bundles within bundles of different components of muscles. So skeletal muscles are striated, and they're also voluntary muscles. They make up a huge amount of your body weight, 40% of your body weight. Of course, this changes depending on what you do. For example, if you're a bodybuilder, you're going to have more muscle than most other people. The 40% is for an average person. So the voluntary part is really important here. And so I'll give you a quick rundown of the nervous system. We are going to focus on the nervous system in a future lecture, but just so that you understand what a voluntary muscle is, long story short, it's a muscle that you can control. So I can tell it to contract, or I can tell it to relax. So when I take a look at a voluntary system, I look at my brain, because that's the control center of your body. So our body's nervous system can be separated into two components. You have your central nervous system, called the CNS, and you have your peripheral nervous system, called the PNS. So your central nervous system, the best way to explain it is the parts of your nervous system that are protected by your spine, your skull, and the blood-brain barrier. So highly protected areas such as your brain and your spinal cord, those make up your central nervous system. But you also need to have a mechanism for the signals that are coming from your brain to reach the peripheral components of your body. So those pathways that connect the rest of your body to your extremities, those are called the peripheral nervous system, or the PNS. So this means a couple things. Number one, the PNS is not protected by your spine or a skull, so it's more prone to injury. Next, it means that your peripheral nervous system carries signals from your brain to your extremities. And that means one of two things. Number one, those signals that come from your brain to different parts of the body, they can be involuntary. So usually those are self-regulating, like how fast your heart beats, to get your lungs to remember to breathe, all that stuff. Or it can be voluntary or somatic. So the muscles, skeletal muscles, are part of your somatic or voluntary nervous system. Whereas your cardiac muscles will be part of your involuntary or autonomic nervous system. So it's here in the voluntary nervous system that these skeletal muscles are going to play a critical role. It's going to help transmit signals from the brain to your muscles and tell them what to do. So in terms of what you will have to know for the course, you'll have to know what happens after your brain sends the signal to move your muscle. And so we're going to go through quite a bit of biology here. Number one, we need to know the breakdown of a muscle. So if I have a skeletal muscle, let's see. So I start off with my skeletal muscle. It's surrounded by, in pink, the epimysium, and it contains what's called muscle fascicles. And within each muscle fascicle, this is surrounded by something like a skin called perimysium, and this contains muscle fibers bundled together. Now you take a look at the muscle fibers, and it's surrounded by another layer of protective skin, let's say, called an endomysium. And this muscle fiber contains something called myofibrils. And those myofibrils are going to contain thick and thin filaments that help your muscles contract and relax. So we're going to take a look at the sarcomere after, because the picture is quite small over here, but it's very important to understand how a muscle breaks down into its components down to the sarcomere. So I have a close-up image of the sarcomere. A sarcomere is basically the basic contractile unit of a muscle fiber. So every sarcomere is composed of two main protein filaments. You have the actin filaments. So let's see if I can. The actin filaments are in purple here. So these long purple strands. These are the thinner filaments, and you also have myosin filaments, and these are thick. So in green, you have these thick myosin filaments that are here. Keep in mind that the actin filaments in purple, they are anchored to something called the Z disc. And so because the sarcomere is one unit of your muscle cell, there's a bunch of sarcomeres that are connected to each other, and they're just separated by the Z disc. One sarcomere is the distance between two Z discs. So here you can see that the myosin filaments in green, they overlap the purple actin filaments. And so there are cross bridges over here that connect the myosin filaments to the actin filaments. Let's see. I want to take a look at the different zones now. So here's another depiction of the sarcomere. So you have your actin filament in blue, and you have the overlapping myosin filament in red. So in this image, at the top, you have a relaxed sarcomere, and at the bottom, you have a contracted sarcomere. You will need to know what all of these are called. So you can see a space in between the two actin filaments. That's called the H zone, and and as the sarcomere contracts, the H zone gets smaller and smaller. And during contraction, both of the actin filaments are going to move towards the middle M line. And then, of course, when it's relaxed, H zone increases, and both sides of the actin filament, they get farther away from the M line. Okay, so now we should probably take a look at how this happens. So in order to understand how this happens, we have to turn to something called the sliding filament theory. So this diagram contains a little bit more information than you would have to know, but you need to understand the general idea of this. And so it would be good to take some notes as to what the sliding filament theory is. So according to this theory, myosin filaments use energy from ATP to walk along the actin filaments so that it allows it to contract. So I'm going to explain how muscle contraction works, starting from muscle activation. So let's start with your brain telling your muscle to move. And what your brain is going to do is send a signal called an action potential, which we'll talk about later on in the course. This action potential is going to stimulate something called the sarcoplasmic reticulum. So I'll write that down here. Okay, so we have the action potential. It sends a signal to your muscles, which stimulates the sarcoplasmic reticulum. And what it does is it stimulates it so that it releases calcium into your muscle cells. So the sarcoplasmic reticulum releases calcium to your cells, muscle cells specifically. This calcium is then going to bind to troponin. So that's a component of your actin filament. So the calcium binds to your actin filament. It causes a change in the configuration of your actin filament, and that allows your myosin filaments to attach to your actin filament and form a cross bridge. So that the next step would be calcium binds to actin, allowing myosin to bind and form a cross bridge. Okay, so that cross bridge is represented over here. So we start here at number 1 in the diagram. We've gone from the action potential all the way down to the first step in this cycle. Okay, so what this cycle represents is a repetitive process of something called a power stroke. So where we start is when myosin binds to actin. When myosin binds to actin, what's going to happen is ATP is going to release, is going to be broken down, just like this. So the ATP is going to be broken down and energy is released. What this allows for is for myosin to do a power stroke and pull the filaments inwards. So that power stroke right here is very important, and that is a repetitive motion. So once the power stroke is done, myosin is then going to detach itself from actin, especially when another ATP molecule comes and binds to it. So you have over here, ATP coming in, binding with your myosin again, releasing myosin from the actin. You have ATP being hydrolyzed, and then the positioning of the myosin head so that it can attach to the actin filament again, but farther down this time. So if I draw another diagram here, this is your actin, and this is your myosin head. So in the first iteration of this process, your actin filament is going to move this way. So this is the original position. And afterwards, the power stroke is going to cause the actin filament to move inwards towards the M line, which is right here. And so as it moves inwards, the myosin head detaches and reattaches farther down the actin filament and produces another power stroke, moving it closer and closer with each stroke. So that general idea is important to know. You do not have to know all the details, but you have to know the general idea that it's a repetitive process, and it's all because of the binding and release of ATP to allow myosin to connect to the actin filament through cross bridges. I'm just going to erase that. Okay, so in terms of the contraction, overall, this contraction is going to last for as long as there is enough ATP and calcium in the system. Once your impulse or the signal from your brain to your muscle stops, the calcium is pumped back into the sarcoplasmic reticulum, and the actin returns to its resting position. So that is going to allow your muscles to lengthen and relax. One of the most important things to understand about the power stroke and just the muscle contraction itself, one single power stroke only results in the shortening of 1% of the length of your muscle. So that's very, very tiny. And if I'm actually if I'm actually contracting and extending my muscle, there needs to be a lot of power strokes happening very, very quickly in order for me to do it so fast. So in order to achieve an overall shortening of 20%, there would have to be 20 power strokes. So in terms of muscle contraction, I believe every time you're contracting your muscle to the fullest, it's a contraction of 35 to 40% of the total muscle length. So you have approximately 30 to 40 power strokes happening every time you're contracting your muscles. Moving on, we want to figure out when muscles contract. So muscles are going to contract when they experience tension or load. So there's several different types of contraction. Number one, you have isotonic contraction. That's when the load remains constant during a contraction. So that's if I'm lifting, for example, lifting this pen up, I'm lifting it up. It's the same weight, but I have constant movement. You also have isometric contraction. So that means the muscle length is constant and the ends are held rigidly. So this would be more so weightlifting if you're lifting something up and holding it in place. That would be isometric contraction. Afterwards, you have latent period. That's going to be the time it takes for your muscle to respond after an external stimulus is applied. So for example, if you're catching a ball or if you're tossing something, there is a slight delay, in most cases very unnoticeable. So that's called the latent period. In terms of locomotion, if we are moving towards biodynamics, we have to consider isotonic contractions. Why? Because it's when the load remains constant, but I'm actually moving. So I don't have a rigid body. If I'm looking at biostatics, keep in mind I should only be looking at isometric contraction because that means my whole body is rigid. But if I have isotonic contraction, contraction is happening and my load is remaining constant, but my body is actually moving. So when we talk about locomotion, we're looking at isotonic contractions in the muscles, and then we can take a look at the rate of contraction. So if I'm contracting my muscles when I'm moving, most likely I'm going to contract more quickly and then slow down as I reach maximum contraction. And I know we're going to be talking about biodynamics later, but might as well finish the discussion of muscle contraction first. So when we talk about the mathematical considerations of contraction, we have to consider two things. Number one, we have to consider length. And so when our muscles are contracting, you can't contract your muscles until it's like 0 centimeters. It can only be contracted to a minimum length of xm. Once we know the minimum length, we'll be able to calculate the rate of contraction, so the speed. So moving on to the rate of muscle contraction, the rate is proportional to the length by which the muscle can be further shortened. So in other words, what we're trying to show through the next slides is the fact that when you're contracting, it must be greater at the beginning and then slowly fall to 0 as it approaches the minimum length. So to start off, we're going to introduce something called the shortening constant, K, and that shortening constant has to be inversely related to the load L. And this kind of makes sense because if my load gets heavier and heavier, on my hand, then my muscle is going to contract more slowly because there's so much more weight that I have to lift. So we can actually come up with a rate equation based on these two values, K and XM. So it's just a proportionality constant. If we assume X is the length of the muscle at any point in time, and XM is the minimum distance that it can be, or basically the maximum, the limit of contraction, then we can say that the rate of contraction is equal to some sort of constant K multiplied by X minus XM. So these equations were actually obtained from an experimental physicist and biophysicist, A.V. Hill. So he actually performed some experiments on this and was able to derive these equations from his data. So once we have that equation, we can also manipulate the values a bit to give us some insight into the behavior of shortening muscles over time. So the question is, can we show that shortening is going to slow down over time as predicted? So what Hill did was he looked at all of the experimental observations that did show that over time, the rate of contraction decreased. So that means that shortening will slow down over time. So if we have the rate equation given as V equals K times X minus XM, there are several different ways that we can modify the equation to give us a different perspective. So the first one is to remember that velocity is the change in distance over the change in time, so we can just replace V with dx over dt. And I won't show the work to get here. You can prove it yourself if you'd like, but if you integrate dx over dt equals 2k times x minus xm, you're going to get an equation in red over here, x equals xm plus the difference in the starting position of the muscle minus the maximum times e to the power of negative kt. So this equation won't be testing you on it. It's just to let you know that it is possible for us to model the behavior of shortening time just by integrating the equation for contraction rates. So what this equation tells me is that x is equal or proportional to e to the power of negative kt. So it means that over time, the distance traveled, or the distance of contraction, is going to get smaller and smaller. Okay, so we're now going to move on to muscle power. And so we're going to take all of the information that we've learned in terms of just muscle movement, muscle contractions, as well as all of the basic foundations in physics that we had gone through earlier in this topic about work and energy and power. So we're going to combine all of that knowledge together to try and derive muscle power. So first of all, we have to consider what is involved in a contraction and how do muscles spend energy. So if I want to take a look at power, it's going to be the total energy done by muscle over time. So I can't just consider the work that muscles do, I have to consider the heat that they release as well, because it is, I am expending energy when I'm contracting my muscles. So there are two things to look at. There's work and heat. So if I'm lifting a load, then I'm doing work. So that work involves macroscopic displacements of a body against gravity. So I'm lifting something up against gravity, I'm doing work. The work done in lifting a load of, let's say, effective mass m by a distance of delta x is going to be given by, and we have our equation that we had before. We have W equals to FD cos theta. If I'm just lifting something directly up, then I have just FD. And cosine of theta, the theta is 0, because if I'm lifting something up, I'm pushing up, and the object is moving up. So both the vectors are in the same direction. So W is equal to FD. The force that I'm applying is going to be equal to the force or the weight of the object, which is mg, because I want everything to be in static equilibrium with no external imbalanced forces. So I want my upwards force to be equal to the downwards force. So if my object has a weight of mg, then I'm pushing up, or I'm supplying a pushing force of mg. So with F equals mg, all I have to do is now replace d with delta x. And so I get an equation, W equals to mg delta x. Now we take a look at the heat that is released from different simulations that have been created. So we can look at molecular dynamics. When your muscle is contracting or working, it's going to dissipate heat that's proportional to the amount of contraction, delta x. We're also going to consider A as an empirical constant. So this is basically a proportionality equation. So delta x is going to be our heat, and it's proportional to some constant A multiplied by the amount of contraction. So when I go to calculate the total energy, I have delta E, which is my total energy, equals to delta W plus delta Q. And so I get mg plus A times delta X. Now, if I want to calculate muscle power, I have my total energy. I can just do P is equal to delta E over T, and I get this equation, mg plus A. So I have mg plus A over here, times delta X over T. But we know that x over t, or distance over time, is equal to v. So we can just replace that with v. So that is your equation for muscle power. Now we have to take a look at something called critical load. Muscle speed, which is v, is going to become 0 once you reach maximum load. What this means is that your muscle can't lift more than that maximum amount. So everybody has their limits. Once you reach that maximum amount, what's going to happen, or as you approach that maximum amount, your speed is going to get slower and slower because it's going to be more and more difficult to raise it up. So by looking at this graph, which was obtained by the researcher A.V. Hill, he noticed that, of course, lighter loads are going to mean faster speeds. And it's because of this that he was able to find a secondary equation to model muscle power as well. So before I leave this slide, I want to mention that in blue over here, you can see the power that's being developed by your muscle as you increase the load. So as you increase the load, you're supplying a lot of power, but as you surpass a certain threshold, your power is going to decrease. Okay, so based on this graph, A.V. Hill saw that the power developed by the muscle really depends on the difference between the maximum load the muscle can lift and the load that actually acts on it. So he created an alternative equation to represent muscle power, where P basically just depends on the difference between maximum and actual load. So using a proportionality constant B, he said P, muscle power, is equal to B times the difference between the two loads multiplied by G. So that's going to be some sort of force, mg, multiplied by a proportionality constant B. So now we have two equations for P. We have the one that we got before with energy or work over time, which is presented here on the left. And we have Hill's new depiction of power, which is B times m naught minus m times g. If you rearrange this equation, you can actually find a way to push all of the constants to one side over here. And once you do, that means that you have A plus mg times V plus B is equal to a constant. And that in itself is called the fundamental equation of muscle contraction. And why is it called the fundamental equation of muscle contraction? It's primarily because you have two terms here. You have m, or two variables. You have m and you have v. And because this is, they're both equal to constants, if I move a plus mg over, it's going to directly indicate that speed is inversely proportional to load. So this provides mathematical and physical proof and a valid theory as to why the speed of contraction is going to increase as you decrease load and decrease as you increase your load. The last thing I want to talk about in terms of muscle power is something called mass-specific muscle power. So we call that EM, and that's the work that's done per unit mass of muscle. So the mass of the muscle is little m, while the entire body's mass is capital M. So if I'm looking at the total energy of a system, and I just want to see the mass-specific muscle work, then I'm going to multiply EM by the total mass, and I should get the total energy. So during locomotion, work is converted into kinetic energy, and we can assume that the average speed of your body is capital V. So if we assume that we have m times EM, that's the total energy, if all of the work from your muscles is converted to kinetic energy, we know that kinetic energy is 1/2 mv squared. So I also know that my total energy is made up of many pieces of mass-specific muscle work multiplied by the total mass. So equating those two together, I'll be able to actually derive an equation for the mass-specific muscle work EM. So that's just mv squared over 2 little m. If I want to determine the amount of power that each small component of muscle provides, then all I have to do is put in PM is equal to EM over T, which is simply this divided by T, and you get mv squared divided by 2mt. So this equation in red is something that you will have to know. You don't need to know how to derive it, but that's given to you just so that you understand where it comes from. Okay, on to the last application for this lecture, which has to do with the strength of your bones. So I'm going to go through the structure of bone tissue, which is a hard tissue or rigid tissue. Then I'm going to go through maximum load and how bones can easily break. And finally, I'll just go through how we usually look at bones from a physicist's perspective. Okay, so before I talk about the structure of bone tissue, I want to mention that there are actually several types of bone in the human body, something that you should remember. There's long, short, flat, sesamoid, and irregular bones. So long bones are basically bones that are long. I don't think it needs any more explanation. Just like your femur, that's a long bone, or your radius. You have short bones, which are roughly cubed-shaped bones that are usually attached to bases of extremities. So for example, the bones of your wrist and your ankles, those are considered short bones. You also have flat bones. Those flat bones are usually very thin and curved, and sometimes they are flexible, sometimes not. Your skull is a really great example of this, but it's quite hard and made mostly of compact bone. The fourth type is sesamoid bone. So a sesamoid bone is bone is one that's embedded in tendons. So something like your kneecap or your patella, that would be a sesamoid bone. Everything else, there's a lot of irregularly shaped bones in your body. Those would just fall into the irregular category if they don't fall into any of the other ones above. The difference between these types of bones really has to do with how much compact bone they have versus spongy bone. So as you can see in this picture, so right here in this picture, if you've looked inside like a bone before, like a broken chicken wing bone or something like that, you'll notice that the outer shell of the bone is super hard and dense, and that's called the compact bone. So it's like the skin of the bone, very hard, very compact, very hard to get through. Now the inside of the bone is very porous, so it's got a bunch of holes. The more you get into the center, the more porous it gets. It's also, because it's porous, that means it's also lighter, so it's very convenient for movement. So those are the two types of bone that make up a bone. You have compact areas and you have spongy areas. The different types of bones that you can have, long, short, and all that stuff, they have a different ratio of compact versus spongy bone. That will obviously change its structural integrity. So we are just going to focus on bones in general. I don't want to go into details about the different types of bones, but in general, I want to talk about the tensile strength of a bone. So biostatics and biodynamics really do depend on bones, because bones are the levers of your body. So for your bone, the structure and shape is going to adapt to its specific function. It's formed by inorganic materials, approximately 60%. It's also fixed within a matrix of collagen, which makes up 40% of its composition. Like I said before, it can be spongy or it can be compact. If we're looking at the compact bone, it actually has a density of 1.9 milligrams per centimeter cubed. So that's quite dense. Bones are also extremely strong. They can be as strong as granite against compression, and 25 times as strong as granite against tension. So they're great for support, and especially for your skeletal system. In terms of breaking a bone, because bones are very, very strong and can stand against high amounts of compression and tension, the only thing that can really break a bone is something that it's not used to. So that thing that it isn't used to is twisting. So if you're twisting a bone too much, called shearing stress, then you can cause stress fractures or eventually a break. So that would be the easiest way to break a bone. Now, in terms of us as physicists looking at bones, we take a look at it as, we try to model it as a cantilever or a beam. So a typical example of a bone is the long bones in your arms and your legs. So taking a look at this diagram on the right, you have your, let me just grab this. You have your long bone here and another long bone here. And what these do is they act as a cantilever that is loaded at both ends. So in this case, there's a cantilever here hinged at both ends, and there's another one and it's hinged here and it's holding a ball, and that's your load. Your cantilever is always a horizontal beam, so we have to model it as a straight line hinged at one end with a load at another. We consider bones to be the lever arms of the system. You can have joints or articulations at each of the hinges, and they provide the mechanical coupling that allows for the motion of one bone with respect to another. So if you have more points of articulation, or basically more joints, you can have more fine-tuned movements, just like with your fingers. Okay, so now I'm just going to go through a summary of what you should remember for this lecture. There's quite a bit of stuff that we covered, so you still have to know some of the details, but in general, you should focus on the difference between biostatics and biodynamics. You should definitely be familiar with forces, torques, work, energy, and power. If you're not familiar with it, then definitely ask questions. I would suggest being able to draw free body diagrams and to practice drawing free body diagrams if you're not used to it. And after you've mastered drawing free body diagrams, try and apply static equilibrium to solve problems. So the first step is going through that practice problem and trying to solve that yourself or with the help of some friends. Next, we talked about muscle tissue. So definitely know what muscle tissue's structure and composition is. Know its method of contraction with all of the steps from sending a signal from your brain down to stopping the contraction. We also talked about muscle power and mass-specific muscle power. I just listed those because it's important that you know the equations for those. Not necessarily how you derive them, just the equations. And afterwards, of course, we talked about bone structure and characteristics. So just make sure you do know some of the biology from that and know that we can easily model bones as levers in our body.